All right, so next we're going to talk about a lot of science today, but once you understand these concepts and can apply them, makes you better. We'll start with this edge over here. So I have you guys hold out your hands. Preferably you don't have a cut in your hands. This is alcohol. Don't smoke right after doing this. Just going to put a little bit in your hand. Just hold your hand out and just let it sit there, and or you can blow across if you want. And then you can think about how that feels. If you don't have a cut, the answer will be the same. If you have a cut, you're going to get a different answer. Just a little bit more for you. Oops. Trying to get this to drop, but it's not quite. Okay. How's that feeling? Cool. What's happening? Yes, it's absorbing heat. The alcohol is changing state from a liquid to a vapor. As it's changing state from a liquid to vapor, especially if you move it, let's speed that up even more. It's evaporating. It's changing state from a liquid to vapor. It's absorbing heat. It's a cooling effect. It's a cooling effect. It's cooling your hand. So Benjamin Franklin did a lot of science experiments studying with alcohol. So Benjamin Franklin, they used rags and fans and whatnot, and they wrapped them around thermometers. They put them around thermometers, put fans and stuff on them, and they were able to get the temperature down to I think it was definitely below freezing. I can't remember what temperature it came down to, but they got it down really low. It was definitely below freezing. I think it was down to like 0 degrees Fahrenheit. A really low number. I can't remember exactly what the number was, but they were able to get the temperature down very low with alcohol and evaporation. And Benjamin Franklin, and all of his brilliance and all the awesome things he came up with, made a quote. I can't remember the word-for-word quote, but it's pretty close to this.
Well, it's possible to freeze a man to death on a warm summer day.
I'm thinking all the really cool stuff he could have thought of. Man, we can make food last longer. We can make ice cream. We can have snow. No, we can kill somebody on a summer day with this. This is great. I can freeze a man to death on a warm summer day. That's Benjamin Franklin's first thought. So that's stuck in my head. So every time we talk about cold and say cadavers or something, that's why I'm thinking of good old Ben Franklin. He's now corrupted my mind. So, but it was with alcohol, because alcohol is a refrigerant. It's changing state from a liquid to vapor. Here's what's happening in the evaporator coil. Refrigerant, as my refrigerant's running through here, my refrigerant is evaporating. The refrigerant is changing state from a liquid to a vapor as it goes through this coil. The heat from the air is making it boil. As it's boiling, it's absorbing heat or evaporating. As it's evaporating, it's absorbing a massive amount of latent heat. Remember that 970? It's not the same number depending on what refrigerant we use, but it's a massive amount of heat that is absorbing into that refrigerant. A massive amount. It's not just that I have low temperature, low pressure, but it's that change of state. That is the magic. The heat gets into the refrigerant, and whatever heat I absorb into the refrigerant, I have to get that same amount of heat back out. So here, it's not just that I have high pressure and high temperature. It's that I'm making that refrigerant change from a vapor back into a liquid, making it condense, making it reject a massive amount of heat. You guys ever been out and had a can of soda or something to drink, and you can see condensation on the can? That is condensing. That condensing means instead of it absorbing 970 BTUs of heat, it's rejecting 970 BTUs of heat. So to prevent that, you have a koozie, right? Now the insulation of the koozie is like really thin. It's very little insulation that's on there. But it's just enough to raise the dew point to prevent condensation. And if I prevent condensation, I prevent latent heat from dumping heat into my cup, container, glass, whatever. Pretty cool, huh? Yeah. So I don't want to prevent condensation. Now, if you see those styrofoam cups, they have just enough insulation in that styrofoam to help reduce or prevent condensation. That's why your ice lasts so much longer.
So that's why, yeah, those are a lot better.
Yeah, because the other ones, it's just the condensation builds up on it, the heat's rushing in, plus the condensation, 970. Now, you're not going to get a pound of water of condensation off your unit, but if you did, it'd be 970 BTUs of heat. 970 BTUs would change the temperature of that water very quickly, or whatever that substance is. Cool, huh? A lot of science involved. But the next thing is boiling. What kind of effect is boiling? Evaporating? A cooling effect. So here, we could call this a boiler, but boiler was already used. So we called it an evaporator. The refrigerant is evaporating from a liquid to a vapor, absorbing heat. Over here we call this a condenser because the refrigerant is condensing from a vapor back to a liquid, rejecting heat. We absorb heat into the refrigerant. I reject heat outside, out of the refrigerant. So far, so good? I manipulate the point at which it boils by manipulating the pressure. Right? Can I manipulate the boiling point of water?
Yes.
Ooh, I hear yes, I hear no.
Yes.
I'm hearing yes, I'm hearing no. I'm hearing yes, hearing no. Let's find out. First off, we have to understand a little bit more about pressure than what we already understand. One thing I want to start with is this glove. If we notice, the glove's tied off. What's the pressure in this glove?
0.
0, right? There's the same amount of pressure inside and outside. But in reality, there is pressure in this glove. There's 14.7 pounds per square inch of pressure in this glove. 14.7 psi. But there's also 14.7 psi of pressure on the outside of the glove. So if there's equal pressure on the inside and equal pressure on the outside, the glove is what we call deflated. Right? So what we're going to start with, I'm going to put the glove in this chamber. You guys may want to circle around here so you can see this. We may have to take turns. If the first group of people kneel down and the second group of people lean over them, and the third ones are standing up, I think we can get everybody to see it. This is why I set the classroom up like this, we can see as much as possible. All right, so that's in my other states I couldn't have this, but Nevada they legalized it, so I could bring this in. So I felt that was okay.
Right. Not very long ago either.
All right, so this is a vacuum pump. All it's going to do is take the atmospheric pressure out of this. We're under pressure right now. We're under 14.7. If you go fishing, a fish in the bottom of the ocean, he's been under pressure his whole life. He doesn't know it. You reel him up, and that pressure, his eyes are bugging out. He's pressurized out. He doesn't know he's under pressure. We don't know we're under pressure until we go up on the mountain, try to do some hiking. There's less pressure. It's hard to breathe. You know, I realize really quickly. So I'm going to take the pressure off so you can see what's happening. There we go. Ish. Safety's overrated.
Oh, geez. That's cool. Well, it's a vacuum.
Vacuum pump. I'm just pulling the air out of this chamber. I've taken and dropped the pressure inside of this chamber. The pressure in the glove is still there, but now that I've removed the pressure on the outside, that 14.7 on the inside is pushing out, and therefore you see it as being inflated. But I didn't put any more molecules in there. It's a pressure difference.
That's cool though.
It is cool. Now if you watch it, keep your eye on it, I'm going to put the pressure back on it.
like a deflating balloon.
We do that with the marshmallows and the
Marshmallows will do it really cool too. The marshmallows will expand.
You need
For
to
sure.
marshmallow then.
There should be a black spray bottle over there. Perfect. And I also need a rag or a paper towel or there's some by the sink if not. That'd be perfect. And got a cup of water.
Just right behind you.
Oh, surprised I didn't knock that over. So what we'll do is put the water in the chamber. Don't matter. Just toss one.
Are you gonna make the water flow?
Oh, that'd be cool. Tie to science guy. The water sometimes makes it fog up. So it'll take us a little bit to get it going. But I'm dropping the pressure, I'm reducing the pressure. Now we're under 14.7 pounds per square inch at sea level, but I'm taking that pressure away from the water. So in other words, I'm dropping the pressure. I need to change the oil in my pot, it's taking longer than usually does. It's about there, it's about to start. Any moments. Getting close.
Oh, it's bubbling.
It is. We're gonna speed this up a little bit. Let's if somebody would take and dump this out and put some warm water from the sink in there, just the bathroom sink, just pour it out, put it about halfway with just warm water, and let me grab a thermometer so we can actually measure this. I'll be right back. The last one didn't survive. We'll get a new one. I go through about 10 of these a year.
Only 10?
Yeah, only 10. I thought that was a good number.
Have you ever done more than 10, like 20?
What? How many experiences have you done in a year?
Done a lot.
Yeah.
Not all of them are this, but they usually require some kind of fire, explosion, or collapsing or something.
So now we all know. We're going to continue doing some safety's overrated, actually.
So is this technically dangerous? Like, could it like pop or something?
116, right on. What was your question?
Like, could this like pop off or?
No, it'll implode if
I was
anything.
just guessing. I didn't know you had a thermometer. I thought you threw that thermometer away.
I threw that one away. This is another one. Why buy one when you can buy a bunch?
1,300,
Just 'cause,
1,314.
It's going up. What I'll do is a pass around. Everybody stick your finger in the water so you can kind of feel like you get an idea what the water temperature is. Because sometimes the numbers alone isn't enough for us. So we'll all feel the water. Hopefully it was water from the warm water faucet, not pee, right?
I didn't have enough time to generate that.
Hopefully you see it time. Oh yeah, I need to take a shower harder than that. You say to wash your hands. Maybe you're right, man.
Yeah?
120. In a restaurant, to wash your hands, gotta be 110 degrees.
Really?
It's like a health. So a lot of people.
At least 110, or that's the number they shoot for?
Yeah, at least.
Okay.
To kill bacteria in your hands.
Interesting.
It stays fresh, it stays fresh.
Learn something new every day.
Heat on the jacuzzi then.
Ooh. If you guys ever get the chance, take a pool certification, CFO class. CPO, yeah, that's what it is. We have a guy that works for us that teaches the class. If you guys want to take it, if we get enough people, we can do a class here. But if you take that class, you learn a lot about pools, and you probably will never want to swim in a pool ever again. I took the class just because I was interested. I've never been in a pool since, especially a jacuzzi.
Why?
Oh, just take the class.
It's the same reason why you don't stick your head under a raging water or something at a water park. Let your imagination run.
I used to worry about the pee, and that's nothing to worry about. Pump struggling. Rah, rah, rah. There we go. Is it boiling?
Yeah.
It is. Just barely?
No, it's
No, it's that's a full boil right there.
There's water going on the top.
Yep, so as it's boiling, it's steam. That steam is condensating on the top of that lid because it's cooler. So that's why I put the anti-fog on there, because otherwise it does it so fast you can't see anything happening in there. So that's what we have going on, the water boiling. Did I add heat to that? No, I just manipulated the pressure. By changing the pressure, we changed the boiling point.
Do the AC units do that too?
Yes, but not with water.
With the cool.
With what?
With refrigerant. So in the evaporator coil, we changed the pressure. By changing the pressure, we changed that temperature. That's enough, I think. Whatever we want.
Whatever it needs.
Is that water like really hot right now or no?
Now everybody fill the water. We'll measure at the end, but don't say anything. When you touch it, don't say anything, but be careful when you touch it. Just don't say anything. Let everybody make your own decisions.
This is gonna be my shower water.
Compared to the last one? What's the temperature difference for all this sticking out here?
Yeah, by the end.
Blue water, channel water.
I'm gonna try it again.
So the water wasn't actually boiling.
It was boiling. We saw it boiling. It was without a doubt. It was boiling.
Oh,
Just as soon as you run it
Since
out.
you released the pressure,
oh,
the
yeah.
pressure went back.
What happened though was the water was boiling. The water was changing state from a liquid to a vapor. The water that did change state was absorbing heat. It was absorbing heat away from the water that was remaining.
Oh.
The temperature is now 98 degrees. We've taken a significant amount of heat out of the water. So boiling is a what kind of effect?
Cooling.
Cooling effect. And I can manipulate my boiling by manipulating my pressure. Right? So when you see water boiling, your whole life you've thought, well, water boiling is hot water. But boiling is not a heating effect, it's a cooling effect. Right? Did we not just boil water?
Yeah.
Did it not drop temperature?
Yeah.
It's hard to unteach yourself some of the things you've been taught, you've been seeing. But if I manipulate the pressure, I can manipulate the boiling point. All right? So far, so good? So refrigerant in that evaporator coil, we manipulate the pressure. By manipulating the pressure, I manipulate when that refrigerant boils. By manipulating when that refrigerant boils, I can make it absorb heat at a low temperature. So even though it's 75 in the house, I can make the refrigerant boil at 40 degrees. Making it boil at 40 degrees, and the air is 72, the temperature of the refrigerant boils at 40, and there's 72 degree air against it. Is it going to boil? Yeah. Is it going to absorb heat?
Yes.
Is it going to change state from liquid to vapor? Ah, we've hit all the main points. That's what's happening in the evaporator coil. That's why I need to drop the pressure on that side. So the same thing, if I reduce the pressure, I reduce the boiling point. Anybody done any cooking in, say, Denver or anywhere up in the mountains? Yeah. What does it take? What's different about cooking there?
You have to cook at a higher temperature, don't you?
Lower temperature.
Longer.
Longer.
Here's why. Right now we're under 14.7. That means there's air stacked on top of this, on top of that, and on top of that. If we go up in altitude, there's less air stacked on top of us, which means there's less pressure. Now, there's less pressure, means there's less pressure pushing against the water, which means water will boil at a lower temperature. I don't know the number off the top of my head, but let's just say in Colorado, let's say it boils at 190 degrees. So it's boiling at 190 degrees. Can you get the temperature of the water above 190? No, because it's just going to boil faster. So if I'm cooking this food at 212 and I'm cooking this food at 190, what's going to take longer to cook the food? 190. There's less heat going into it. It's cooling itself off. So I have to cook it for longer at altitude. So as you go higher in the mountains, your water will boil faster, but it takes longer to cook.
Yes.
Right? It's crazy, right? It's the same thing as my vacuum. I removed pressure and made water boil at, what was the temperature, 72 degrees or 100 degrees? I made water boil at 100 degrees. That's 112 degrees less than what we know it boiling at here by changing the pressure. Now, can I do it the other way? Can I make the water boil at a higher temperature?
Yes.
How?
Change the pressure.
What do we do with the pressure? Increase the pressure.
Yeah.
If I increase the pressure, I raise the boiling point. If I lower the pressure, I lower the boiling point. So in your car, you have a sealed system and it's pressurized. And in your car, you keep it under high pressure. Anybody know what their car runs at? The temperature gauge on there? About what?
It should average about between like 210 and 220.
But water boils at 212, right? So we pressurize it. By pressurizing it, we prevent it from boiling. Now the problem is, if it's at that temperature and you open the cap, you've reduced the pressure. Now it's immediately boiling, and as it's boiling, it's spraying that water and that gas all over and you get burned really bad. But by keeping it under pressure, you keep the boiling point higher. So I can have that water at a much higher temperature, and it's not changing state. And the same thing goes with cooking. One of the things that made Colonel Sanders so famous was not just the secret sauce, but the fact that he could cook his chicken in a pressure cooker. He increased the pressure by a high amount, and he could cook the chicken a whole lot faster. And by cooking that chicken faster, he was able to make more money. And so that's when we cook with pressure cookers. By pressurizing it, if I put big latches on here and increase the pressure to a whole higher number, the water's not going to boil until, say, it gets to, I'm just going to throw a number out there, say 300. Well, at 300 degrees versus 212, which is going to cook faster? 300. So by having a pressure cooker, I can put the heat into that food much faster because my boiling number has been pushed up higher. I can put more heat into it. You've been cooking your car, everything is with refrigeration. I need to get a pressure cooker just for that.
Yeah.
That'd be a good point. I'll put it on my list. Yeah? She's able to cook faster, right? Yeah.
Would it change drastically if you were if you had a basement?
No, you need
You need actual drastic like.
you need bigger changes.
Yeah.
Yep. So as my pressure decreases, my temperature decreases. When you go up to Mount Charleston, you feel a temperature decrease, right? Yeah. You also have a pressure decrease. As you come down, you feel it getting warmer. There's more pressure. So there's immediately a pressure-temperature correlation, but there's also a saturation boiling temperature correlation. Okay? So far, so good? All right. Now let's talk about water is a refrigerant. Let's talk about a better refrigerant. I'm going to bring over a refrigerant bottle, and we can go back to our chairs.
I feel manipulated.
Warping the minds. Oh, sorry. Oh, let me do this way. Okay, so this right here won the war, they say. The World War II, they said that they had big battles with these. I don't know, I don't get it, but...
Battle of the Bulls.
Tanks. I didn't say they were good jokes. I told people, I said, look, I'm gonna quit air conditioning and become a comedian HVAC instructor. And everybody laughed. But 8 years later, nobody's laughing now. Okay, so this for the longest time was the most popular refrigerant around. We learned that the problem is that this refrigerant destroys the ozone layer that protects us from the UV rays from the sun, and realized that's probably not a good thing. There was 132 countries during the 80s. Now, a lot of you guys are way too young to remember the 80s, but during the 80s, it was a very rough place. You had Germany split between North and South. People that tried to see their families outside the wall were being shot. East and West, that's right. Sorry, East and West, yes. It was a very violent place. You had Cambodia that was back to ground zero, to where they had killing fields that killed millions of people at a time. No country trusted anybody. There was controversy. There's so much going on all over the world. There was no trust anywhere. There's all kinds of battles and wars. We had the Cold War going on. It was crazy.
Bad hair.
Bad hair, decent music. Hey, so it's a bad thing. But in the 80s, 137 countries that didn't trust anybody, 137 countries came together and said, you know, I don't trust you, and I don't trust you. I don't like and I don't trust you. But you know what? If we lose our atmosphere, we're all going to die. So 137 countries came together, and now it's a lot more than that. But they said, hey, look, this is destroying the ozone. Let's reduce this number so that we don't all die. And that way we all have land. I can steal your land later, but I can't steal it if we don't have ozone. So they come together, and 137 countries signed the Montreal Protocol in the late 80s, and they decided that many years later they were going to do away with this refrigerant. And today, that day is finally upon us, and you're going to hear people say, well, why are they forcing this on us? As long as I've been in air conditioning, when I got into air conditioning, I knew that this was going away. Now, regardless of what you believe and don't believe, I got into air conditioning 1995, and it was years before that we knew that this refrigerant was going away. They had phase outs, they had plans, it was a decided thing. Now you get people in and go, well, they're taking away our refrigerant. It's not a new thing. We knew it was coming for a long ways away. People just keep pushing it off. But this is and has been the most popular refrigerant. There's many other refrigerants, but this is just one example of many. So this refrigerant has a temperature pressure guide, and they have these for water also. So right here on this board is a temperature pressure guide. So R22, this refrigerant right here, at zero pressure, R22, 0.5 is as low as I can go. I'm going to move over to the left. At 0 psi, it's about minus 40. So what's the pressure here? 0 psi gauge. If I was to take this refrigerant, turn it upside down with the liquids at the bottom, and I was to open this valve and spray it on you, it would be at minus 40. The refrigerant would be boiling on you at minus 40 degrees, violently boiling from a liquid to vapor, absorbing a massive amount of latent heat. So not just that it's minus 40 on your body, that it's boiling, absorbing heat away from your body, minus 40 degrees. You'd be instantly frozen.
So it's so-called time.
It's even at minus 40, there's a lot of heat still left in it, but it's absorbing a lot of heat out of your body. It would be doing massive damage to your body. Anything I sprayed would instantly freeze. It would just turn instantly to ice.
When do we get to see that?
We don't. And the reason is,
We all want to live.
for every one molecule of R22 will destroy 100,000 molecules of ozone. So if I was to release this, and I release, say, a pound, that's 100,000 pounds, just roughly, of ozone that would be destroyed, and it takes a very long time for that to ever recover, and it's illegal, and it's a $27,500 fine, and I think it was 10 or 15 years federal prison. So we're not going to see that ever, but there's other ways to see it, and we'll talk about that later.
YouTube.
Minus 40. That's the boiling point of refrigerants at 0 psi. What if I was at some temperature lower than minus 40? Is that possible? Let's think of...
160 to work with.
That's right. Let's think of Alaska. It gets below minus 40 in Alaska. So if I was in Alaska, let's